It is AP time, and we're dancing in the city. It is AP time, and we're singing everything is great and fine in the intergalactic time. Greetings. A message from your overlord. Okay, we'll wait for some people to get in here. I'm gonna try to draw that sailboat again. Get better at sailboat drawing. Terrible at it. Oh, you know what? I bet I could draw with some highlighter calligraphy like this. Oh yeah, look at that. Calligraphy magic. Mr. Lord. Mr. Lord Resthob. Wait, that curly thingy up there looks stupid. Let's make it cool. We'll do it like a filigree star. Oh, I kind of like that. Nah. Ooh, that's cool. That's cool. Intergalactic. Whatever. That still looks really cool. I've never drawn prettier lines in my life. Look at that. Look at that R right there. That R is to die for. Can I even do that again? I can't even draw that again. This is like that purple. I see that's. Oh, how did I do that? I can't even do that again. I'm not gonna erase that R for the rest of this segment. I can't do it. It's just too beautiful. Make sure to dodge everything. Okay, I guess we'll just leave that there then. Because everybody knows how good of a letter R. This is such a good letter R. Look at it! Okay. What was I doing? Oh yes, we're doing physics. That's right. That's right. I got this. Okay. Greetings. We are looking here at charges and doing work. That is what we're at in the classroom. Let's take a look at a quick example real quick. This is technically your homework problem. I'm not going to spend too long on it because I don't want life to get too easy on you. It's technically your problem, right? Let's make this a little easier on me. Okay. Parallel plates. In between these parallel plates, you have a number of wonderful uniform field lines. And we talked about this at the end of class. We all know that I'm a terrible line maker. We all know that these are uniform and that they start at one side and terminate on the other. And because I never specified it, we will call this the side of, I don't know, positive 100 volts, and then we'll call this 0. Okay. If we have a particle moving in here somehow, either a proton moving this way if the electric field is doing work, or an electron moving the other way, let's find the amount of work that is done on this proton moving across. Now, if you remember today in class, we had the equation on the board that QV, and remember there's a tiny delta right in there because it's a change in voltage, is equal to the negative work. Okay? This means that if we were to look at this and figure out, okay, if we got a proton here, and remember, that would then have a +1 standard electric charge. We could say that 1.6 times 10 to the minus 19th coulombs times our voltage difference, our final position minus our initial position, that would be like 0 minus 100 volts equals the negative work. Okay, so we'd have here is 1.6 times 10 to the minus 19 coulombs times negative 100 equals the negative of the work. Or the way we could do this is we could just move this negative sign over there. Notice when we do that for something where you're going and grounding out, that essentially cancels out, and we do find that we have a positive number for the work done by the electric field, which is a great thing because the electric field would do positive work on a proton. Okay. On the flip side of things, if we had an electron, we saw in class today, this would have read 100 minus 0 because it's going that way, but in the end we'd end up flipping due to negative signs. So we would see that for a problem like we had tonight for the homework set. Okay, so that's a standard way that an electric field can kind of do work in that regard. Okay. I'd like to once again point out, look at this letter R here. It looks so good. Anyways. Okay. That's basically as easy as it gets in terms of looking at work done by electric fields. It can get harder, but it's not really that much either. We'll see this in class in the next few days, that because voltages are scalars. Remember last time we had a problem that we had something along the lines of like there's a charge here, there's a charge here, and then there was something along the lines of like, what's the E field out at this point? And it was a real pain because if we're testing this with a positive charge, the E field would like push away, but it would also pull down, and you'd have to break this up into vectors. This problem gets really easy whenever here's a thing and here's a thing, positive and negative charge, and what's the voltage out here? Because now all you do is you say, okay, what is the voltage from the red thing plus the voltage from the blue thing? We're done. That's it. You just walk away. Super easy. If you're like, well, how much work would it take to move an object there? You just say, okay, remember that net voltage I have? If this is the voltage, I'll just multiply it by Q. We're done. And that's it. Where last time when we had these E fields, it was like, I'm going to break it up into vector components. And you had to do work here, and then you had to do trig. You were like, oh, I got to write SOHCAHTOA. And then you had to like redo a Pythagorean theorem. You don't have to do that. You just have to do 1 voltage, 2 voltage, add them. That's the net voltage. You've got 100 particles, just find the voltage due to the 100 things. Add them. It's a scalar. It makes everything so much easier. Okay? We will talk about that in class, but it's something just to remember. Literally for voltages, you just add them all up. The only thing that gets kind of weird with voltages is every once in a while you'll have a problem like this here, and it will say how much work is done from bringing, you know, a test charge all the way out at infinity into this point. And what you have to remember is that the potential that you're looking at here, and really if we're thinking about the amount of work in that regard, I guess we'll put a negative there. If we're talking about work, this potential out at infinity is 0. So when you move it in, you're going from 0 to a more negative value, and you can just think of it as saying, okay, I'm going from a 0 voltage plate to some negative number voltage plate, and boink, I've arrived. That's it. That's all the problem is. It's actually the same problem as this one up here, which was really easy, right? But now it's like, oh, we're coming from infinity, and we're coming to this point, which is a sum of many, many charges creating a voltage at that point. Who cares? Infinity 0, we know what this is. Can we just add them up because it's a scalar? And then thump thump. We're done here. Can we go home? Yeah, we can. Okay. So be aware of that whenever we're doing the voltage and scalar stuff. This is personally one of my favorite sections of the year because it is a scalar, and voltages are nice and easy as we're doing electrostatics. Things get a little bit harder with voltages whenever we start talking about circuits, but that's just because circuits we look at a little bit differently than just static point charges. Okay. Since nobody's here again, I will once again refer us up to this letter. Look at that R. I get one more shot at this. Nope. One more. I feel like I'm trying at it too hard now. No, it's just the most perfect handwriting I'll ever have. Like, even look at this Z. Oh, it's beautiful. Okay, well, anyway, because nobody's ever going to be able to write this nice again in the history of mankind, good night, everybody. Have a good one.